Okay, so here we see the percent by country who feels supported by relatives or friends at any time. Number one, we just need the percentage for US, so we find the US. You may want to move these labels over to the right side so you can gauge where it is, but it should be about 89 or 90%. One of the things you'll notice on the chart, it doesn't start at 0, which can be a way that people are manipulated by charts, or it could be just a way to show the data more clearly. And I think that's Google's logic behind doing it here. So we're comparing the Germans and South Koreans. If you find the Germany bar, it's about 92%. The South Korea bar is about 76% feel supported. Divide those two, notice the percents cancel out, so there is no percent on this 1.2. In other words, Germans are 1.2 times more likely to feel supported than Koreans, even though notice that this Germany bar is pretty big and this Korean bar is pretty small. That's just because the scale doesn't start at 0. So in general, when you're creating graphs, make sure you either start at 0 or you have a good reason not to start at 0. Number 3 is our confidence interval question. And so this is an actual number. 88.2% of the people in all of those countries, that's our population mean, that percent feels supported, at least based on the data we have. And then this is somewhat of an estimate, but roughly a standard deviation of 20 or 20%. So we're now taking a sample. We want to know about EMU students in general. That's the population we're now concerned with, and our sample mean is our class average, which was 92.3%. And you may wonder, well, how's that an average? Well, everyone had a value 0 to 1. 0 if you didn't feel supported, 1 if you did. And we really took the average of all those zeros and ones, and ours was 0.923 or 92.3%. So again, you can do this entire problem in terms of percents or in decimals as long as you're consistent. I'm going to do it here keeping the percentages. So we have 92.3, that's our sample mean. The sigma, the standard deviation here, is given as 20%. So if you use 0.20, you need 0.923 here. Our sample size is 26. So you'll notice we had 26 students, 24 said that they did feel supported, but our sample size is really everyone that we're getting data from. So that would be 26. And then probably the hardest thing here is getting this 1.64. So if you set up a normal distribution, and we want a 90% confidence interval. So we want 90% of the distribution in the middle, and then that means there's 10% left over. 5% down here, 5% down here. And if we look on table A, we're looking for the z-score that'll give us 5% of the normal distribution to the left of our z-score. So we're looking at 0.05 because we have the percent, the proportion, we're looking here, and then we'll trace it to the outside to get that z-score. So 0.05 is going to be in between these two numbers. Either one is fine. Negative 1.64 or negative 1.65. And if you looked up 95%, by the way, that's the 90 in the middle plus that 5% on the left, you'd get a positive 1.64. It really doesn't matter which you use in this formula because you're doing plus and minus anyway, it'll cancel out. But the 1.64 is the important part. If you multiply this times the 20, divide by square root of 26, you'll get your error margin of 6.4. So that's our flexibility where we know that our class is ranking it at 92.3%, but we can't directly assume that all EMU students, 92.3% of all EMU students, feel supported. So here's that plus or minus flex room. What we can say now is we're 90% confident that percentage of EMU students who do feel supported is somewhere between 85.9% and 98.7%. That is assuming that this is a random sample, that our class is a random sample of the entire EMU student population, which probably isn't true. Question number 4, we're doing a hypothesis test. So now what we're doing is we're looking at EMU students versus all of the people in these 30-some OECD countries. So we're going to need to pull some figures here from number 3. Let's go through step by step. Step 1, we need the null hypothesis. The null hypothesis would be that nothing is going on. In other words, there's no difference. There's nothing that's effective. In our case, are EMU students different from people in OECD nations? No, they're not. And so the mean would be if EMU students really are no different from OECD nations, then the average for EMU students would also be this, just like the average for the OECD nations is, and we're pulling that from question number 3. The alternative hypothesis, so if it turns out that if we reject this, we need some plan B. We need something to fall on. If EMU students are not like OECD nations, then what? Are we saying that they're just different in that they could be lower, they could be higher percentage? Are we forcing it to be lower? Are we forcing it to be higher? Here's where we have to look at the question itself. So this question was, are EMU students different from? In other words, we didn't specify whether they'd be lower or higher. We just said, are they different in either direction? So we use the not equal to. If it said, are EMU students lower than, lower percentage of EMU students than OECD nations, blah, 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 that would be a less than. But because it says different from, that would be not equals to. So now we're going to go through a test this null hypothesis. If we get evidence against it, we'll reject it and settle on this alternative scenario. Step 2, we're looking at our critical values or rejection. It's basically our target, what we're shooting for with our particular sample to see if we do have evidence to reject our null. And we can set that up in 2 ways. One would be the alpha of 0.05, that's given to you right here. The other would be to get the critical z. So what that critical z would mean is we're looking for the cutoff that we need our z-score to be. This is a target, and then this is our shot that we're taking at the target. So how do we know what that is? Well, we take this 5% or 0.05, and we either put it in one tail or two tails, depending on what we set up as our alternative. So here we gave ourselves the opportunity to reject either down low or up high. So we split that 5% into half, and we look this up on the chart, 0.025, or maybe you happen to remember that it would be 1.96 from doing the confidence intervals. Next, step 3, we actually take our shot. So we look at our sample, which was 92.3. The null hypothesis mean, in other words, what our mean at EMU would be if we're no different from OECD nations. We set up the standard deviation over square root of sample size here, just like we did. Notice that 3.92 is the same as what we had in our confidence intervals. There's a very close relationship between these two. And if we work that out, we get a z-score of 1.05. Our sample, in other words, is somewhere about right here. In order to reject the null hypothesis, we needed to get beyond that z-star. We needed to get further out into the tail than the z-star. We did not do that. So we can say that we did not reject right away. But let's also calculate the p-value here. So this is our particular z-score. And what we want is to look at the tail. The tail would be the area that's more extreme than our sample. if our z-score is on the right side of the graph, that tail, that small part of the distribution, will be to the right. If we're on the left half of the distribution, the tail, the small part, will be on the left. So in our case, it's right here. So we're looking at this on a chart. So you're getting the 1.05, finding this value in table A, 0.8531, but that would be the distance, the area here in the region up until our z-score. 85.31% of samples of this size would have sample means less than our sample mean was. And we don't want the body, we want a tail, so we subtract this number from 1 to get 0.1469. That's the proportion of the sample means that are our z-score or even higher. But that's one tail. That's one tail. We need to ask ourselves, do we want to add in a second tail here? And that's where we have to take a look at our alternative hypothesis. If we said that we were going to potentially reject in either direction, then we have to double what this value was because we need both tails. If we just did one direction, if we just did less than, or if we just did greater than, then we would just take that single tail and that would be our p-value. But since we need both sides, we take 2 times that number to get 0.2938. That is above our alpha value of 0.05. Remember, p-value low, null must go. We did not get a low p-value, and so we failed to reject. Whether you look at the p-value or compare the z-score to our z-star, either way we failed to reject. In other words, we were not able to come up with convincing evidence that EMU students are different significantly than the OECD residents in general. 5 is just a matter of looking these up on the chart and then giving an explanation. 6 is the central limit theorem. So central limit theorem tells us the distribution of sample means will have the same mean. It will be a normal distribution, and it will be the original standard deviation divided by square root of sample size. So in our case, the sample sizes were 36. So square root of 36 would be 6. So our new standard deviation will be 1/6 of the original standard deviation. Question number 7 is just comparing a single score to the distribution of Mcat scores. And so we set up just a simple z-score like we did back in chapter 3, not the one where we're dealing with sample means here. We get a negative 0.46, and this would give us, looking that up in the table A, would give us the area to the left, but we want above 22, so we take 1 minus that value to get 0.6772 or 67.72%. 8 is just the definition of p-value, so the results we got or more extreme if the null hypothesis is true. Number 9, confidence. So this first one's not correct because this first confidence interval is just one of the many different types of confidence intervals we could get. It could be an extremely low one, it could be an extremely high one. We have no guarantee that the means of our samples will be in there. In fact, even the means of your population, we don't know. The estimated population means we don't know will be in there. Single sample, we can be actually 100% confident that we'll catch the sample mean because the confidence interval is built around the sample mean. Here, this is one way of looking at confidence intervals, a correct way, and this is another one. So these are two similar but both correct ways of looking at the confidence interval. Number 10, this first one is incorrect because you'd always like as large of a sample size as you can afford. It's never going to hurt you to have a larger sample size. This one you don't need to specify the direction. However, B, C, and D all do point out legitimate critiques of the statement, things that they got wrong, and explains why.